So we come to our last speaker, who is Professor Qiangfei Xia. He's a professor at the University of Massachusetts, Amherst. Let's welcome Qiangfei.
Okay, good afternoon. It's great to be here. It's the first time in Aachen. In the past few months, all the emails I received from my Professor Wasser is, please make sure you are understood by the broad audience because we have engineers, we have biologists, neuroscientists, etc., etc. So in the next 35 minutes or so, I'm trying to explain what we have been doing in the past decade with no phase diagram, no energy band diagram, and absolutely no differential equations. So AI certainly is everywhere nowadays, and there's also made a lot of noise in the media from 7 years ago, the AlphaGo game, and to nowadays, even an elementary school student knows about ChatGPT. But what really behind is the energy consumption in a hardware. Nowadays, according to a DOE's estimation, the computing takes about 10 to 15% of the electricity worldwide. But if we do not change anything in the computing architecture, by 2040, the electricity production in the entire world is not going to be sufficient for computing only. That's a serious problem. Number two is the environmental or the carbon footprint. According to estimate by my colleagues at UMass, to train in kind of a medium-sized model transformer only have over 200 million parameters. We're going to emit the carbon dioxide, which is going to be equivalent to that from 5 US cars. So that's going to impose a huge problem in the sustainability of our society. Number three is really the cost. We all talk about GPT, right? If you are using the GPU to train your ChatGPT model, say this is actually an estimate I took from a paper, and if you use the GPU to train the GPT-3, which has 175 billion parameters. You know, NVIDIA right now, they are really red hot. They probably high demand in terms of HX 100, but they also provide services. You can buy the hours, right? You can pay probably $1.50, and then you train your model. If you added that up, you're going to have about nearly $10 million to train a GPT-3 model. That's a lot of money. Certainly, that's basically says the AI is only going to serve the super rich, and let alone that if you want to train the GPT-3 model, and then you also need to consume about 700 kiloliters of water, including the system. So the fundamental reason behind this is really the purely hardware. The digital computer was not tailored for AI computing. On the architecture level, the von Neumann architecture was still the backbone of a lot of computers we are using. In this architecture, we have this memory unit, and the process unit is physically separated. As a result, we're going to have to shuttling the data back and forth through more than often. It's very limited bandwidth of a bus here. This is, to the extreme case, it's like you have multi-way of traffic, but only you have a single lane road. You have to wait over there, and then it's going to impose the energy consumption and also the latency issues. On the transistor level, we have been following the Moore's law and dynamic scaling for over 50 years. And then when the transistor becomes smaller and smaller, they're not going to listen to us. The operation is going to be degraded or even destroyed. Also, when we pack more and more transistors in a certain area, you're going to generate a lot of heat. So these are the problems with the traditional hardware based on the digital computer. There are certainly a lot of solutions proposed at different levels, from the new materials, different state variables, new novel devices, and also novel architectures. For example, nowadays, there are certainly two very hot topics. One is quantum computing, which promises exponential speed up for certain tasks. The other one is neuromorphic computing, which aims to model the processing elements on neurons in the brain. So we are not trying to build a brain, right? We actually do not understand our brain well enough, but we do understand. Part of it is, number one is we interface with analog information, and we do the computing where this information is stored, or in other words, we do in-memory computing in our brain, and we certainly can learn. And we also use spikes, which is the in a biological neuroscience world, that's the action potential to represent information, especially the timing of the spikes. And from the fundamental level, those spikes really worked on the ion channels in the neuron. So in order to solve this problem, certainly we need what? We need a device that can better emulate the biological counterpart in our brain. And here comes the memristor. So similar to a resistor, it is a two-terminal device, but different from the traditional resistor. It is nonlinear. So on the left, you can see if you measure the regular resistor, you get a linear IV curve, especially when you read them out with a relatively low voltage. In the middle is a typical IV curve for a memristor. You can see this hysteresis loop, which is nonlinear. And this device also has very simple structure. More than often you can find there's two-terminal device with two electrodes and then a switching layer sandwiched in between. So this is a we rely on the resistance switching behavior. And this resistant behavior actually was first observed in the 60s in silicon oxide, aluminum oxide, et cetera. But back then, what we were trying to do is trying to perfect transistors. So we want to remove all these kind of defects in the oxide and try to get a perfect transistor behavior. So that behavior certainly get ignored in the community for 40 years until 2008, a group at HP Labs led by previous speaker, Stan, who linked the resistance behavior with a theory postulated by Leon Chua in 1971. So the fundamental mechanism for switching is really we have the ions, either anions or cations. They are localized, or either they're distributed at interface. And then you can think this is basically they are localized dopant inside of a switching material. That's going to change the resistance of the material. We can tune the distribution of the ions, and then we can make them analog. So that's on the device level. We need a device that works on the ionic motion to emulate our human brain. On the architecture level, you know, in the AI, most of the resource demanding computation in the AI is really the matrix operation. So for example, this is a chart I borrowed from a paper published by IBM. Let's say 85% of the resource in a typical neural network is allocated to the operation of the matrix. And then in the digital world, you can see if even for a very simple vector matrix multiplication, you will have to move the data and then do the computing one by one and then move it back to the memory. So you will have a lot of energy consumption to moving the data around. So there is certainly an analog way for this is using the analog crossbar arrays to do the analog vector matrix multiplication with the laws of physics. Say, for example, in this case, we have a crossbar array. At each point, if we use the tunable and non-volatile conductance of, let's say, a memristor to represent the weight, we are going to be able to direct interface the analog input, for example, voltage. And for multiplication, we use Ohm's law because at each cross point, we're going to generate a small current according to Ohm's law. In mathematics, Ohm's law is, multiplication, right? And then we can measure the current along each column according to Kirchhoff's law. That's summation. And then the beauty of this is we can design a circuit and sense the current out of all the columns at the same time. As a result, we're going to do the one-step analog vector matrix multiplication regardless of the size of the array. With all this, we can boost the power efficiency and computing throughput substantially. So that's why in 2012, 2022, if you have heard the keynote talk by the Turing Award winner, Geoff Hinton, he suggested, quote, we can use very low power analog computation. You can use trillion-way parallelism using things like memristors for the weights. But we need a good device. There are certain challenges on the device level. We need multi-level resistance levels. Each of them should be stable so you do not worry about the drift of the weight. And then we need to program or recommission them. You need to have certain endurance. And we use Ohm's law. We need IV linearity, et cetera, et cetera. There are also other challenges on the circuit and architecture level. But last but not least, we want to make sure if the technology needs to take off, at this moment, we want to make sure they are foundry compatible. So we designed a device based on the hafnium and tantalum oxide. It's a very interesting structure because when we talk about multi-component device, we always would think they're multi-layer, right? But in this case, what we have is a concentrated or localized tantalum oxide channel embedded in hafnium oxide matrix. These two oxides, they're both available in foundries. They have the pros and the cons. Tantalum oxide has great thermal stability. It's going to stay as amorphous at, let's say, 800 or 900 degrees C, but it's very chemically reactive. If you make circuits, you do not worry only about the device itself, right? You worry about the surrounding materials such as passivation, et cetera, et cetera. Tantalum oxide is going to react with silicon nitride. It's going to degas into silicon oxide, et cetera, et cetera. So we need to protect this tantalum oxide, and then we use hafnium oxide because it certainly has, you know, a very, very good chemical stability. It's not going to react with the surroundings. So with this device, we have achieved very low switching voltage. It's also get very fast switching speed, very great endurance, and very, very long retention. We also measured this device, the multiple resistance levels. They stay at stable even at relatively high temperature. Now that we have this device, and what we need to do is we need to make them into circuits. And then if you don't want to build an array, usually we need a selector, a device called a selector. But for now, the selector device is not ready. It's at least for the computing purpose. So we still adopt this traditional 1T, 1R architecture. So in each cell, we have one memristor connected head-to-head with a transistor. Transistor has been around for more than 75 years. It's mature, and then it's certainly a good device. We can use it as a selector. Furthermore, we can very precisely control the channel conductance of the transistor. As a result, when you want to program this cell, we can control the voltage dividing effect very precisely. And certainly combining the, let's say, the mature infrastructure in the IC industry we have been writing on in the last few decades, and the novel properties of emerging device is the way to go. So this is actually the first integrated circuits with memristor and a foundry-made CMOS. That was made in HP Labs when I was fresh out of graduate school. Writing onto that experiments, we made larger arrays. The practice is usually you design the passive transistor array, send it out to a foundry, and then you take it back and do the back end of the line integration in this case, is a university lab at UMass. And we can achieve very high yield. Even at the university lab, we achieved 99.8% of the yield. And then we have different size of 1T1R arrays from 128 by 64, 64 by 64, et cetera, et cetera. By the time of the publication, that was still the largest analog array. Now we have the array, we need to program them and then do the computing. And then in the early days, we built the system, which is all off-chip. So in this case, we first collaborated with John Powell in HP Labs and built a system which encodes the information, the input information with the voltage amplitude. And we later went on and built another system which uses the pulse width or pulse number to encode the input information. So with this system, we're able to have 128 input into the chip, and then read out 64 channels in the same time. And then, as we just mentioned, the input can be voltage amplitude or pulse numbers. And then we use probe card, which is right over here, to talk to the array. Still, this is certainly it's going to take a lot more power if you talk about the power perspective. But if you are trying to screen what your device stack is, what is your device statistic is like, gives us a lot of flexibility because you do not have to worry about the ADC and DAC on chip yet. Although for now we already have moved all this into a single chip. So when we do the programming for inference system, what we care is the precision of the programming. So in this case, we usually use multiple pulses using a feedback circuits to control the tolerance range of the conductance. If it's over-programmed, we reset a little bit. If it's under-programmed, we set a little bit more. So that means in each cell, probably you would need more than one pulse, sometimes hundreds of pulses. But for inference system, once you program, the weight is there, you use it for many times, so you do not really worry about that. So for example, on the upper right, you can see the conductance of a 64 by 64 array evolves with the programming cycles. On the lower right, you can see they have very narrow distribution, which means we can get comfortably 8-bit precision or 64 levels. With this system we built, we can see that we can have 64 stable levels. We also get excellent linearity, and we have the linear and symmetric weight updating and improved uniformity with the 1T, 1R architecture. Surely the transistor helped tremendously in all these aspects. Now that we have the array, we want to use it for edge intelligence applications. And say, for example, in this case, we use what you're seeing here on the left is the 128 by 64 1T, 1R array. And we use probe card, so the Docker's part along the four sides, they are the 388 probes which you landed at the same time to these arrays. With that, we're able to program any algorithm inside of this array and to do a lot of interesting computation demonstration. For example, if you use this as a single layer, you can do the DCT, discrete cosine transform, and we use that for the image compression. You can partition them into two layers of perceptron and use it for MNIST classification. If you partition them into one fully connected layer and one long short-term memory, we use that for gate classification to identify a person by the way he or she walks. And finally, we partition them into three fully connected layers and implemented the reinforcement learning algorithm. This algorithm came out of our friends in computer science department in the early 80s at UMass, and now this is one of the two major algorithms used in both AlphaGo and ChatGPT. So the one point I want to make here is certainly this is for computing purpose, right? The requirements on the device property, it is very different. To the extreme case, we want to show even this device is not a good memory per se, it can still be used as an excellent computing engine. For example, on this array, it's 128 by 64 array. It even have nearly 11% of defects. What you can see, if you think this is a memory, this is a very lousy memory. But was with this kind of defective array, we used it for MNIST classification. We can still achieve over 91% of accuracy. This basically says one thing is the different requirements from between the memory and also the computing applications. Actually, we talk about noise, we talk about variation. For computing purposes, a little bit of variation noise is absolutely necessary. For example, we did a simulation shows the recognition accuracy for MNIST is going to increase if your variation increase from 0 to about 1%. Of course, it's going to drop if you introduce too much of that. This is really because when we were trying to do the classification, we used the stochastic gradient descent algorithm. In that algorithm, what we're trying to do is trying to find the global minimum. If the device is too ideal, more than often you're going to start with the local minimum. With a little bit of variation, it's going to take you out. So that's actually a very interesting finding here. So what's the state of the art? In the next couple of few slides, I'm going to update you where we are. In terms of the programming precision at single cell level, we have achieved over 2,000 conductance level, or equivalent 11 bits. In this case, what we did is really trying to introduce a denoising process. When we set the device, the conduction channel sometimes is incomplete. Sometimes you have some kind of isolate islands there. Those are the charge trap centers. In the denoising process, you either remove those centers or combine them into one. As a result, the random telegraph noise you're going to have is going to be much reduced. So that's why within the certain conductance range, you can pack more conductance levels there. In terms of the physical scaling, we have demonstrated that the device can be scaled down to 2 nanometer by 2 nanometer in a crossbar array. We developed a technique called the nanofin. If you want to make the device extremely tiny, what you worry a lot is the series resistance or the wire resistance from the electrode. We develop a technology we can have a wire resistance which is lower than 100 ohms per micrometer, which is 10,000 times more conductive than a single word carbon nanotube. We can do a very simple demo to store some information in this smaller array. We also believe going 3D is the way to go. So we built A layers of the tantalum hafnium oxide device into 3D is the convolutional neural network for video processing. The lower is basically shows the edge detection. It's a very simple demo. We just program two private filter kernel there, and then we can test the edge of the video. So going 3D is certainly have a number of advantages. Most natural one is you're going to pack more devices inside, but that's probably the least important one, right? And from this morning to now, we believe that with the 3D, we can have much better connectivity. The reason our brain can work that great is really because of the number of the neurons that has the huge number of the connectivity with the neighbors, and our brain is actually 3D. And then from the machine learning perspective, with the third dimension, we have the flexibility to reconfigure some neural network topography. In this particular case, you can see this staircase, right? This is really, we were trying to program the convolution, the stride, okay, into the staircases in the convolutional neural network. And last but not least is, when most of the neural network nowadays is two-dimensional topography. That means if we have a 2D input, we often have to unroll the data into one-dimensional vector and feed it, for example, from the west of the neural network and read it out from the south. And the unrolling process itself takes a lot of resource. If we have a three-dimensional neural network like this, say if we have an input out of the image sensor, which is 2D matrix, right? We should be able to do the matrix to matrix multiplication in one shot in the analog domain as well. So last, for the commercialization, we're really trying to take this technology out of the research lab to the industry. So this device derivatives and also the process has moved to commercial foundries. On the left, this is a 12-inch wafer out of a commercial foundry. And this is the CMOS was based on 65 nanometer node. And then on each die, you can see we have the 10 arrays, each of them 256 by 256. And then they are designed by 8 bits. And then we have all these peripherals, including the DAC, ADC, transimpedance amplifier, et cetera, shrink into one of those arrays. And then with each chip, we have 10 arrays. They talk with each other through a RISC-V processor. On the right is basically the first generation of an evaluation kit. And then right under here is one of those chips shown on the left. With this, we have demonstrated a lot of interesting applications, including the AR, VR, and we can use it for people detection, for keyword spotting, et cetera. With 65 nanometer, we have achieved 85 milliwatts of power and better than 20 TOPS per watt efficiency. This is our first generation. The next generation would be based on 22 nanometer CMOS technology. It should be coming out very soon. As we what we know, the ultimate power efficient computing is really the human brain. So now next I'm going to switch gear to a slightly different device. Um, you know, we have about 100 billion neurons in our brain. Each of them are connected to 1,000 to 10,000 neighbors through a synapse over here. And when we were generating the information and communicate the information, all this, you know, on the physics level is based on the movement of ions, right? We have sodium ion channel, potassium ion channel, et cetera, and then on the other hand, our device, memristors, also worked on the movement of ions. So the natural similarity in this structure inspired us. We probably can use this device to build neuromorphic hardware. This is certainly just get started. And we design a device which we call diffusive memristor. Structure-wise, it's again is a two-terminal device with two electrodes with a switching layer sandwiched in between. Different from the device I just shown, okay? This device is volatile. That means if you apply a voltage, you can turn the device on very fast. You remove the voltage, it goes back to its original high resistance state automatically. And then if you look, you use electrical pulse for this. Say, for example, over here on the lower left, the red is the square pulse, the voltage pulse you applied, and it takes a little time for this device to turn on. We call that a delay time. And then once you remove that voltage, and this you know, current is going to relax back. So that's we call the relaxation. So this delay and relaxation, has a lot of rich dynamic that can be taken advantage to emulate the biological neurons and synapses. A little bit on the device physics level, what we have here is really when we have the device under BIOS. So this is a snapshot taken from the in situ TEM. So we apply a BIOS on one of the electrodes. When the device is on, you can see a narrow silver filament, the bridging the electrodes. That's the on state. Once you remove the BIOS, those silver filament, they are going to retract into the spherical shape to minimize the surface energy. So that's really the fundamental reason why the device can be turned on and then automatically relax back. And then we use this to build the artificial synapses and neurons. In this case, in terms of the artificial synapse, we use two memristors. One is this volatile diffusive memristor. The other is the non-volatile drift memristor. And then we use this, demonstrated a lot of plausible principles in synaptic plasticity. For example, and in this case is the spike timing dependent plasticity. You can simply think this diffusive memristor as a dynamic voltage divider or a timer, right? So without going into details, right, you can think when we have this guy turned on and then remove the voltage, it's gradually going to relax to the high resistance state. Depending on where the next pulse is, the voltage dividing between these two devices are going to be dynamic. As a result, how much synapse weight is going to change on this non-volatile device is going to be very, very different. So that's basically the idea of using this device as a timer and then demonstrate the spike timing dependent plasticity with only two memristors. We further demonstrated that even with one diffusive memristor, we can emulate the ion channel. So in this case, you can see this is the schematic of an ion channel. This is the channel. We use diffusive memristor to emulate the channel. And then the circuit model is on the upper right. You have the diffusive memristor here. You have the parallel capacitant over here. And then on each of the plasma membrane, we have the resistance as well. If you apply a pulse train, which the voltage of the pulses are not sufficiently high, you're not going to turn this device on, but you're not doing nothing there. You actually are charging the capacitor right over here, the parallel capacitor. Once the charge build up across this capacitor is more than enough, the voltage is going to be high enough. Once it's higher than the threshold voltage of the diffusive memristor, it's going to be turned on. As a result, you're going to see the spike of the current go through the resistor. At the same time, you're going to the device is going to discharge. So this is, as we just mentioned, is just the very, very beginning. We are trying to use this to demonstrate the functionality of the leak integration and fire as neuron. If you want to build large-scale spike neural network, there's still a lot of work needs to be done. Say, for example, the uniformity needs to be improved, and more interesting, the time scale of this device. As we have heard this morning, in our brain, we have the neurons that works at slightly different frequency. Maybe we have 10 times difference in different zones of our brain. If we could tune the frequency range of this diffusive memristor, we can certainly implement in a lot of very interesting spiking neural network algorithm. So, to summarize, we have introduced a non-volatile device based on tantalum oxide and hafnium oxide, and we tailored this device for in-memory computing purposes. We built large arrays and then integrated into the SoC and demonstrated a lot of very interesting edge intelligence applications. We also introduced a volatile device, which is a diffusive memristor, as the biorealistic emulators for synapses and neurons. This is certainly a very interdisciplinary area. We need to work together between engineers, mathematicians, neuroscientists, et cetera, And finally, I would like to thank the current group members and past group members, and also my collaborators, especially Joshua, John Paul, and Stan, with whom I started the collaboration since late 2007. And this work is sponsored by federal agencies and industry. And last but not least, I would like to thank you very much for your attention. I would be happy to take any questions you have. Thank you.
Okay, thank you very much. And before we take questions, I want to remind you that we have the poster session after this. So please, go ahead.
Thank you for your nice talk. I'm Zhong. I work at Max Planck Institute. I'm curious about your 3D structure of memristors. Could you explain what's the techniques to make that, and what's the time that it consumes for such a device?
Okay. That's a great question. Since we work in the university with very limited access to the facility, we use the brute force approach to build it layer by layer, photolithography, e-beam lithography, layer by layer. So a graduate student spent 2 years to build that array. We do not expect that to be the case in industry. Once it scales to the industry, it should be much, much faster.
Hello, I'm from Budapest Technical University, and my question would be that in such a 3D structure, how do you solve the heating problem? So I would expect that such devices have an optimal temperature for working properly.
Okay, great question. Heating problem in 3D structure. In this particular case, we have a common electrode, which is metal, that can be used as the heat conductor as well. But on the other hand, because we are using the memristor device as the synaptic weight in that 3D, you would probably expect more the heating problem during the programming stage. But once it's programmed, it becomes a passive array. And then when you read with a lower voltage, you do not worry about the heating that much as compared to an active device. If you need, or especially non-volatile device, if you need to supply the voltage constantly to keep that state, you worry about lot more about heating. But certainly that's a legitimate question. We do need to worry about the heating if you scale it up to a much, much larger scale.
Hello. Thank you for the interesting talk and breaking down the components for doing neuromorphic computing. My question is related to the scaling of memristor that you showed. You showed something like 2 nanometer cross 2 nanometer memristors. My question is, can you also, when these memristors are used in 1T1R structures, can you also scale the transistor to that level such that they can support the currents required for set and reset processes? And how does that work in 3D integration? Because, yeah, how do you integrate transistors in 3D? Thank you.
Great question. It's about scaling of the memristive devices, right, into the new physical domain. For the 1T1R, right now, most of the practice right now is really building the memristor on top metal layer. So that actually has very, very large spacing over there. That's not going to give you the highest density. To scale that 1T1R array, we need to move to lower metal layers. Of course, in a lower metal layer, you get much finer pitch over there. And then you also have to address a lot of associated issues, not just about the pitch, the voltage, and also you have to worry about the thermal budget, et cetera, et cetera. In terms of the voltage, down to 12 nanometer, we are still good. We are still good in terms of the voltage that can be supplied through the 12 nanometer node I/O, not the core voltage. Okay, for 12 nanometer, the core voltage is only 0.4. If you want to program device or even form that, you may need 1.5. That can be supplied by the AL voltage, which is 1.8. I hope that does answer your question.
Actually, I was more worried about the current requirements, because to set or reset a memristor, you would want certain amount of current, and that needs to be, supplied by the transistor. So if you scale the memristor down to 2 nanometer cross 2 nanometer, can you scale down the transistor to that size, such that your 1T1R actually scales down? Yeah.
Let's put it this way. Either current or voltage, you can always design a designated set of circuits for programming. And it is not a problem in the inference anyway. The voltage is low, the current is low. And then we can afford that designated circuits, even you have some extra on the circuits, because our main application is really for inference. Okay? Once you program it to the certain level, with the stability of the conductance levels of this device, you do not worry about too much about refreshing. It's going to stay there for a very, very long time. So overall, the energy landscape is still looking very good.
Do you have time? Okay. Hi, Qiangfei. Thanks for a nice talk. I mean, you can decline, but I just want to know a bit more about the TetraMem architecture. Like, for example, are you really doing in-memory computing, or is it weight storage? That's one. Secondly, for the 8-bit weight precision, are you doing bit slicing, or is it true analog storage?
Okay, I can only answer the question from the technical perspective. Okay, the second part is the 8-bit. 8-bit is not bit slicing. It's a single cell. We can go to 8-bit comfortably for the larger array. Okay, more than often the limit is really if you get a good analog designer or not. Especially, it's going to be limited by the ADC. If you have a very good ADC designer, you can get a high precision ADC, which is available in industry anyway. You do not worry about the system bit precision.
But Qiangfei, just to confirm, I mean, I'm not worried about the ADC part. It's more about the 8-bit. Is it like you're doing 8-bit precise computation using one resistive RAM device?
Yes.
Okay, that's impressive. And it's true in memory compute?
It is doing the in-memory computing, yes.
Okay. Thank you. And you encode in a differential fashion, I assume, right? The weights, that means 2 devices.
Depends on the application, right? For neural network with negative weight, we do use 2 approach. In the university, we always use differential pair. And then in the SOC, where I just showed, there is a reference line there, which is going to save you some space in terms of circuit area.
Okay, thank you.
Maybe one last question.
Hi, my name is Nouridine Zemal from Institut des Matériaux de Nantes, France. I have a question on crossbar. I was wondering how you managed to solve the problem of scenic path current, because during the writing the programmation, you might be not addressing the right cell, the designated cell, maybe.
It's a great question. The question is about a sneak path current, right? So in the most of the work I showed here is really based on the 1T1R architecture. So that means in each cell you get a transistor there. The transistor is going to serve as the selector. So you do not really worry about the sneak path current because you can turn on and off of this device depending on what operation you're going to be doing on that cell. Does this answer your question?
Yeah.